All right, welcome back to the deep dive. You know how this works. You bring us the dense stuff and we dive deep. Today we're tackling a paper that you said really turned the AI world on its head. Attention is all you need. Coming straight out of Google Brain and the University of Toronto. No small potatoes there.
Right. I mean, this paper, it's not just some incremental step. It presents a whole new way of thinking about how machines understand and generate sequences, things like language, and it's all about attention. That's the core idea.
So just to set the scene for everyone listening, before this attention is all you need revolution, what were the main players in the sequence modeling game?
Well, the paper makes it clear right from the start, recurrent neural networks, your RNNs, especially the heavy hitters like LSTNs and gated recurrent network, those were top dog. They were the state of the art for, well, pretty much anything involving sequences. Language modeling, machine translation, you name it. And the way they worked, they processed information one step at a time, like each input influenced the next calculation, creating these hidden states based on what came before.
Okay, so it was all very sequential, very step-by-step. But then, what were the bottlenecks? What was holding these RNNs back?
Well, the problem was kind of baked into the approach. Because everything was so sequential, you couldn't really parallelize the computations during training. Like, each step had to wait for the one before it, especially with long sequences. So it was slow, and it just didn't scale well. The paper actually says this directly, that the sequential nature precludes parallelization within training examples, which, for those of us who like our AI training fast, that's a problem.
Yeah, you're building on the last piece, so to speak. Makes sense why that would be a limitation. Now, the paper also talks about convolutional neural networks, CNNs. Weren't they supposed to be good at parallel processing?
Yeah, CNNs, they offered a way to process chunks of the sequence simultaneously. There are models like the Extended Neural GTU, ByteNet, and ConvS2S, all using convolutional layers as their workhorse. But here's the catch. CNNs struggled to grasp connections between elements that were far apart in the sequence. So relating a word at the beginning of a sentence to one at the very end, that was tricky. The more distance you had, the more operations you needed. ConvS2S, it's linear, so the further apart things are, the more work you got to do. And ByteNet, it scales algorithmically, so a bit better, but still a challenge.
Gotcha. So RNNs, slow but okay with long-range stuff. CNNs, faster but struggled with the distance. So then, enter the transformer. What was the big idea, the one that really flipped the script?
Okay, so imagine this. Ditch the recurrence, ditch the convolutions. Just focus on the relationships between different parts of the sequence using what we call attention mechanisms. And boom, that's the foundation of the transformer. It's about understanding how different words or elements relate to each other directly.
Just attention. That sounds almost radical, to throw out the old guard like that. But you're saying this allowed for a huge leap in parallel processing.
Exactly. With attention, you're looking at all the connections at once. You don't need to wait for the previous step to finish, like in RNNs. So all these computations can happen in parallel, and that speeds things up dramatically. The paper states this pretty clearly. It allows for significantly more parallelization. Think of it like trying to understand a whole picture. With attention, you can look at all parts of the picture at the same time, rather than scanning it bit by bit.
And the results, they kind of spoke for themselves, didn't they? I remember reading about some pretty impressive improvements in both the quality of the translations and the speed of the training.
Oh yeah, the paper boasts about setting a new high score on the WMT 2014 English to German translation task, a BLEU score of 28.4. And this was better than any previous model, even those fancy ensembles that combine multiple systems. Plus, they got there with significantly less training time and computational resources. Their base model, it trained in just 12 hours on 8 P100 GPUs. That's pretty wild. And their bigger model, the one they called Big, that took about 3.5 days but got a score of 41.8 on English to French. So yeah, big win.
All right, so the transformer is this new architecture, all about attention. Let's break it down. What are the main components, the nuts and bolts?
Okay, at its heart, it still uses the familiar encoder-decoder structure. So the encoder takes the input sequence, let's say a sentence in English, and turns it into a bunch of continuous numerical representations, like a secret code. Then the decoder takes this code and uses it to generate the output sequence, in this case, the translated sentence in German. The decoder, it's autoregressive, so it uses the words it's already generated to predict the next one, kind of like, predicting the next word in a sentence.
Got it. And both the encoder and decoder, they're made up of these stacked layers, right? I think the paper mentions NET6 layers in the base model.
Exactly. It's all about stacking. Both the encoder and decoder, they've got a stack of identical layers, 6 in their standard setup. And each encoder layer, it has two main sublayers. First, you have this thing called multi-head self-attention, and then you've got a position-wise, fully connected feed-forward network. The decoder has those two as well, but it throws in an extra one, a multi-head attention mechanism that specifically looks at the output from the encoder.
Okay, so multi-head self-attention, that's a mouthful. Let's unpack that. What exactly is attention in this context, and why is it self, and why does it have multiple heads?
Right. So attention, in the simplest terms, it's like how we focus on certain parts of information while ignoring others. Imagine you're reading a book. You're not processing every word equally. You're focusing on the words that are most important for understanding the meaning. So in the transformer, attention is a way for the model to figure out which parts of the input sequence are most relevant for generating the output. It does this by assigning weights to different parts of the input based on how well they match what the model is trying to predict.
So it's like a spotlight, highlighting the key information. And what makes it self-attention?
Self-attention means that the model is comparing different parts of the same sequence to each other. It's like the sentence is looking at itself to understand the relationships between the words. For instance, in the sentence, "The cat sat on the mat," self-attention would allow the model to see that cat is the subject of sat and mat is the object.
Okay, I'm getting that. So the sequence analyzes itself. But what about those multi-heads? Why multiple?
Multi-head attention, it's a clever trick. Instead of just doing one attention calculation, you do it multiple times in parallel with each head focusing on different aspects of the relationships. So it's like having multiple experts looking at the same sentence, each picking up on different nuances. In the paper, they use 8 heads. And then at the end, they combine the results from all the heads to get a richer understanding of the relationships in the sequence. This, as the paper nicely puts it, allows the model to jointly attend to information from different representation subspaces at different positions.
Gotcha. So it's like getting different perspectives on the same information. Now, the paper also mentions scaled dot product attention. Is that the specific type of attention that happens within each head?
You got it. Scaled dot product attention, that's the heart of it. It involves calculating dot products between vectors representing the queries and the keys, which essentially represent different parts of the input. Then they divide this by the square root of the dimension of the keys. The scaling is there to prevent the dot products from getting too big, especially when you have a lot of dimensions. Then a softmax function turns these scores into probabilities, so you know which parts of the input to pay most attention to. And then these probabilities are used to create a weighted sum of the values, which are also vectors representing the input. It sounds complicated, but it's really elegant, and importantly, it's fast and efficient to compute.
You said fast and efficient. Is that because it can be done with matrix multiplication?
You know it. The paper points out that dot product attention is much faster and more space efficient in practice than other types of attention, like additive attention. And that's thanks to good old matrix multiplication, which modern computers can handle like a champ.
Nice. Okay, so we've got the attention part down. But the paper also talks about these things called residual connections and layer normalization. I always hear those terms in deep learning. What are they doing in the transformer?
Those are essential for keeping things stable and helping the training go smoothly. Residual connection, they're like shortcuts in the network. They allow the gradients from the loss function to bypass some of the layers, making it easier for the model to learn, especially when you have many layers stacked on top of each other. And layer normalization, it helps to keep the activations of the neurons within a reasonable range, which again helps with training stability. They apply these techniques around each sublayer, so it's like wrapping them in a protective layer.
Gotcha. Kind of like safety measures for a deep network. Now, we talked about the encoder with its multi-head self-attention and those feed-forward networks. The decoder, it has those, plus this extra multi-head attention layer that looks at the encoder's output. So how does that one work?
Right, so in this layer called encoder-decoder attention, it's all about connecting the input and the output. The queries come from the decoder, meaning they represent the parts of the output being generated. And the keys and values, they come from the encoder, representing the input sequence. So basically, the decoder is looking at the encoded input and figuring out which parts are most relevant for generating each part of the output. It's how the model translates the information from the input into the output.
So the decoder's like, hey, encoder, what you got for me? What should I focus on here? And the encoder's like, here's the good stuff, pay attention to this. And then there's also self-attention within the decoder, right? But with a twist, I think.
You're sharp. There is self-attention in the decoder, just like in the encoder. But here's the catch. The decoder can only attend to the words that have already been generated in the output. It can't look ahead because that would be cheating, right? So they use this technique called masking to prevent the decoder from attending to future words. It's like putting blinders on the decoder so it can only see what's already been written.
Makes sense, keeps her honest. What about those position-wise feed-forward networks we mentioned earlier? They're in both the encoder and decoder, right?
Those are the workhorses. They consist of two linear transformations with an ELU activation function sandwiched in between. And the key thing is they're applied to each position in the sequence independently and identically. It's like giving each word a little private processing unit, if you will. And these transformations, they're different for each layer, but within a layer, every position gets the same treatment.
So each position gets its own personal massage, so to speak. And then finally, we have the embeddings and that last softmax layer to make the actual predictions.
Exactly. So just like many other sequence models, the transformer uses these things called embeddings, which are basically vectors that represent words or parts of words. These embeddings capture the meaning and the relationships between words, and they feed these embeddings into the model. The output from the final decoder layer goes through a linear transformation and then a softmax function, which turns it into a probability distribution over all the words in the vocabulary. So you get a bunch of scores, and the word with the highest score is the one the model predicts. And a little tidbit. They share the weight matrix between the input and output embeddings and the pre-softmax linear transformation, and they scale the weights in the embeddings by the square root of the model's dimensionality. Just a little trick for better performance.
So the model takes the input, embeds it, processes it through all these layers, and then spits out a probability distribution over the vocabulary. Pretty cool. But here's the big question. With no recurrence or convolutions, how does the model know the order of the words? That seems crucial for understanding language, right?
You're inching on a key point. Since the transformer processes everything in parallel, it has no inherent sense of order. So they have to explicitly tell it. That's where positional encoding comes in. These are special vectors that are added to the input embeddings, and they basically encode the position of each word in the sequence. It's like giving each word a little tag that says, hey, I'm the third word in the sentence, or I'm the 10th word.
So it's like giving each word a sense of place. And these positional encodings, they're based on sinusoidal functions, right? Those wavy things.
That's right. They use these sinusoidal functions to create the positional encodings. And the cool thing is, these functions create patterns that depend on the position. So the model can learn to understand relative positions, like this word is 2 positions after that word. They even tried using learned positional embeddings where the model figures out the encodings on its own during training, but the sinusoidal ones worked just as well, and they might even be better at generalizing to longer sequences.
So it's like giving the model a little bit of a cheat sheet about word order, but in a way that it can learn from. All right, we've covered a lot of ground here. Now let's zoom out and talk about why the authors were so excited about self-attention. What advantages did they claim it had over the old RNNs and CNNs?
They laid out several key benefits. First, computational complexity. You see, for a sequence of length n and a representation dimension d, self-attention is about OK in terms of complexity. Recurrent layers, they're OKMDA, and convolutional layers are OKNDA, where k is the size of the convolutional filter. So when the sequence length is smaller than the representation dimensionality, which happens a lot, self-attention is actually more efficient than recurrence.
And for really long sequences, they had that idea of restricted self-attention, right, to keep things manageable.
Exactly. They knew that OWA could get out of hand for super long sequences, so they proposed limiting the attention to a neighborhood of R words around each position. This reduces the complexity to OS. It might not be as good at capturing super long-range dependencies, but it makes working with huge texts a lot more practical.
Got it. So more efficient in many cases and also adaptable for super long sequences. What was the second big advantage?
Parallelization. Remember how we talked about RNNs being slow because everything had to be done step by step? Well, self-attention, it's a whole different story. It has a constant number of sequential operations, meaning you can do all the computations in parallel. That's a huge speed boost. RNNs, they're stuck with ON sequential steps, and while CNNs are also O1, they often need way more layers to capture long-range dependencies, which slows things down in the end.
So self-attention wins the speed race. And the third advantage was about those long-range dependencies, right? The relationships between words that are far apart.
You're right on the money. Self-attention has a constant path length between any two positions, no matter how far apart they are. That means the model can directly connect any two words in a single step. RNNs, they have to go through all the intermediate steps, which can be a real pain for long sentences. And CNNs, their path length depends on how many layers you have, so it can also be quite long. This path length for self-attention makes it so much easier for the model to learn those crucial long-range relationships, which are the essence of understanding language.
Right, like figuring out who he refers to in a long, complicated sentence. And there was also a point about interpretability, wasn't there, that self-attention allows us to peek into the model's thinking.
Oh, yeah, the paper has these cool visualizations in the appendix showing the attention patterns the model learns. You can literally see which words the model is focusing on when it's generating the output, and you see it picking up on semantically and syntactically related words, even when they're far apart. It's like the model is showing its work, which is pretty awesome for understanding what's going on under the hood.
That's so cool. All right, let's switch gears and talk about training. What kind of data did they feed this beast, and what was their training setup like?
They mainly used two massive machine translation datasets, the WMT 2014 English-German dataset with about 4.5 million sentence pairs and a bigger English-French one with around 36 million pairs. They pre-processed the data with byte pair encoding and word piece tokenization, which breaks down words into smaller units. And they grouped the sentences into batches based on the number of tokens, aiming for around 25,000 source and target tokens per batch to keep things efficient.
And what about the hardware and training time? We're talking big data here, so it must have taken a while.
They used a setup with 8 NVIDIA P100 GPUs. Pretty high-end stuff back then. The base model trained in about 12 hours, doing 100,000 steps at 0.4 seconds per step. Their big model took about 3.5 days, with 300,000 steps at 1.8 seconds per step. So yeah, not exactly something you'd train on your laptop.
Definitely not. And they used the Atom optimizer, right, with that fancy learning rate schedule.
Yeah, they went with Atom, a popular optimizer, and tweaked its parameters for the best performance. But the learning rate schedule, that's where it gets interesting. They started with a really low learning rate and gradually increased it for the first 4,000 steps, like a warm-up phase. And then they slowly decreased it as training progressed. It's like starting slow, getting up to speed, and then easing off as you approach the finish line.
Smart. And they also used some regularization techniques to prevent overfitting, right, like dropout and label smoothing.
You bet. Overfitting, that's the bane of every deep learning enthusiast. So they used dropout, which randomly drops out some of the connections in the network during training, making it more robust. They used a dropout rate of 0.1 for the base model, and they also use label smoothing, which makes the model's predictions a bit less confident, again, to prevent overfitting. They actually found that label smoothing hurt perplexity, which is a measure of how well a language model predicts the next word, but it improved translation accuracy.
So all these techniques working together to train a powerful but well-behaved model, and after all this training, what were the results? Did the transformer live up to the hype?
Oh yeah, it smashed it. On that English to German tab, the big transformer got a BLEU score of 28.4, beating every other system, including the ensembles. And their base model, even that got a score of 27.3, which was still better than anything before. On English to French, they hit 41.8 with the big model, a new state-of-the-art. They also used some tricks during inference, like averaging the weights from the last few checkpoints and using beam search to generate the translations.
So it clearly lived up to the hype, and they did some experiments to see how different parts of the architecture affected performance, right, like playing with the number of attention heads and the dimensionality of the vectors.
Yep, they messed around with the architecture to see what works best. They changed the number of attention heads, the size of the key and value vectors, the model size, and the dropout rate. They found that having the right number of attention heads was super important, not too few, not too many, kind of like Goldilocks. And making the key vectors smaller, that hurt performance. Bigger models did better, no surprise there. And dropout, well, that's always important. They also confirmed that their fancy sinusoidal positional encodings worked just as well as the learned ones.
So they did their due diligence, and the results were solid. And they even apply the transformer to a completely different problem. English constituency parsing, which, for those who don't know, is about figuring out the grammatical structure of a sentence.
Right, constituency parsing is all about trees and phrases, not exactly machine translation. They trained a 4-layer transformer on this task, using both a standard dataset and a much larger semi-superbacked one. And get this, they got some amazing results, even beating some super fancy parsing models. It really showed that the transformer wasn't just a one-trick pony, it could handle different types of structured prediction tasks. They also mentioned specific hyperparameters they use for parsing, like the maximum maximum output length and bean search settings.
So a real multi-talent. Okay, to wrap things up, what's the big takeaway, the key insight that everyone should remember from Attention is All You Need?
The big revolution, the core idea, is that they built a model called the transformer that relies entirely on attention mechanisms. By ditching recurrence and convolutions, they unlocked the power of parallel processing, making training faster and allowing the model to learn those crucial long-range dependencies. And the results, well, they speak for themselves. New state-of-the-art in machine translation, and a clear sign that this attention-based approach has a lot to offer for other sequence tasks as well.
It's a whole new way of thinking about sequence modeling. Now, here's a thought for our listeners. This paper showed the power of focusing on what's important through attention and moving away from strictly sequential processing. So how might these principles apply beyond the world of AI? Where else do we see a need for this kind of selective attention and a move away from linear thinking?
That's a great question. Think about it. Attention is at the core of so much of what we do. How we learn, how we solve problems, how we communicate, how we make decisions. It all involves focusing on the right information at the right time. And the transformer, it shows us that this selective attention can be learned and implemented in a very efficient way. So where else could we apply this? Could we design better learning environments that adapt to individual students' attention spans? Could we create tools that help us filter the information overload we face every day? Could we build systems that understand and respond to our needs in a more nuanced and intelligent way? The possibilities are really endless. The key is to start thinking beyond the linear, the sequential, and embrace the power of attention.
Food for thought. That's the deep dive for today. Thanks for listening, and we'll catch you next time for another deep dive into the world of cutting-edge research.
See you next time.